So we have a slightly different flavored talk in that it's going to be about accelerating applications using smart NICs. And in doing so, what are the challenges that we encountered and still have them? And what are our thoughts in making it a homogeneous system? I'll probably try to define my words. So what we have attempted and what we still need to do. So this is our talk outline. The talk is going to be a bit biased towards telco requirements. So we start off with the telco requirements for NFV, and a bit once again at the edge, because the edge is where the action is today. And the requirements at the telco edge are a bit different from, let us say, at the CPE side or at the core side. So we start with that, and I'll tell a bit of our design philosophy. We started with a pure DPDK x86 software-based approach, and then we had some considerations and why we came to SmartNIC. And my colleague, Barak, would then talk about an FPGA-based SmartNIC from Ethernity, and what is that approach towards the acceleration. So the mid part of the presentation is going to deal with the SmartNIC-based approach integrating with DPDK. And then we take up a couple of use cases, the one with a BRAS or a BNG to be more specific, and look at the system considerations, the system architecture aspects, what we have done. So that's the overall outline. So here, again, this is purely from a telco perspective, a whole big picture. What does a telco require? So all this concept of NFV and Vnfs, the white box disaggregation is great for telcos. And one of the key things that they want is homogeneity. So just as software on an x86, any VNF on an x86 gives them a perspective of the infrastructure is disaggregated and decoupled, software runs on it, and with the DPDK packet processing, the same is continued. But when we extend this concept with additional hardware acceleration, let us say with a SmartNIC, how is that homogeneity maintained? It doesn't become heterogeneous. So that's one of the concern aspects and needs to be fixed. And then the devices need to be programmable and not fixed function. So we have, when we say the next to SmartNICs, what do we have? Be it an ARM-based or be it an FPGA-based. And there are other considerations from telcos from a scalability, which needs to be elastic, which is more from a software VNF perspective. And then the cost aspect. So there was one comment from the previous speaker that load balancers, for example, there are cases where you need software-based load balancers and provides a better cost margin. Likewise, there are cases where a hardware accelerated solution provides a good cost margin from a telco's perspective. So yes, solution, let us say a software-based solution, needs to scale, be it for the low end, medium end, and the high end. And how is it that it can scale seamlessly across different implementations? That's what a telco needs from a deployment perspective. So that's the key aspect. And then the bottom few, they are the edge-specific aspects that we have seen. Some of the key ones, for example, multiple applications. So it is the case of VNF sharing. So far we have seen cases that a VNF exists on a server, uses DPDK, all the resources are there for the VNF, but very often in an edge case, there could be something for, let us say, a BRAS application, and there could be an intelligent offload that is also happening. Let us say a smart city application that would also need to leverage the SmartNIC. So when multiple VNFs from third-party vendors come in, what is the way to coexist? So these are some of the considerations. And again, looking at a generic model now. So this model that I have shown is the one that industry is familiar today. And the telco case, it is referred to as the CUPS model, control plane, user plane separated model. Be it any telco application, be it a BNG, be it a EPC, or be it an emerging, let us say, a 5G front haul application, The intent is to have a disaggregated control plane and a data plane, and ideally, if possible, a control plane works with any other data plane. But today, that's not the case. A VNF vendor, for example, would provide a VNF, both a control plane VNF and a data plane VNF that works one-to-one. But the goal is that at least on an underlying hardware, let us say it's just a server or a server with a smart NIC, the hardware should be shareable potentially by multiple VNFs. So this is the goal and this is an intent. And today, when telcos want to deploy solutions, they look at whether when I take smart NICs from A, B, C, D, and then I have control plane VNFs or VNFs from A, B, C, D, and can they coexist? Can I have a complete compatibility across VNFs and the smart NICs? So that is one of the motivations here. So when we started our kind of applications, VNFs on DPDK, it started with the kind of a traditional architecture. So the control plane, a hardware abstraction layer, so to say, with the DPDK was implementation, one VNF, for example. But then we realized that, say, for scalability or for some reason, we need to go into a decoupled, disaggregated model. We call it as a first-level disaggregation. But then what is a need is that there would be multiple smart NICs, and there would be data path implementations which are, in a way, data plane dependent, and as I said earlier, multiple control plane VNFs. So there would be an association at a vertical level between a control plane VNF and its data plane VNF, but then this part, each data path VNF should be able to work with multiple smart NICs, for example. So this is the motivation from a software side. A control plane VNF works with any data plane, and a data plane like a smart NIC is able to host any other control plane as well. So this is the homogeneity that the service provider is looking at. So at this point, I would invite my co-speaker, Barak Perlman, to take over.
Thank you, Kalimani. Can you guys hear me? Okay. So what we've done until now is discuss about the motivation. Now I'll try to explain what is a smart NIC and how we can use smart NICs and DPDK to accelerate virtual network functions. So I'll start by defining what is a smart NIC. Everybody calls smart NIC different, so I'll give my definition. So I took this slide from a heavy reading report. My colleague in one of the webinars from heavy reading proposed this slide, so I took it. Heavy reading defines smart NICs as the concept of programmable NIC. So each NIC provides the same functionality. If you insert it into a server, you get network connectivity. But the question is not if you can do offloading, all the NICs do some offloading. Is this programmable? Meaning, if sometimes in the future we'll have new requirements of new features, will you be able to program the smart NIC on the fly and provide new functionality? We all know that looking into the future, we're going to have more and more features, more and more requirements for offloading, and that's the idea of a smart NIC. So a typical smart NIC has an I/O controller, could be embedded inside one ASIC or two separate ASICs, and some programmable element. In this diagram, I drew an FPGA. I'm not sure how many of you are familiar with FPGAs. FPGAs are field programmable gate arrays. These are hardware devices which are programmable in the field, meaning you can reprogram the entire device in a few seconds and give new functionality to the hardware. So it's not a CPU-based device. It's a hardware device. It's written in Verilog and VHDL, the ASIC devices, but you can reprogram it on the fly. So an FPGA provides some programmability for the smart NICs to provide new features and new functionality along the way. And another option for smart NICs could be a multi-host CPU offload, like an NPU-based or multi-core-based. Those are providing the same functionality, but in a different manner. So FPGA or which one is this one? Sorry, no.
The other one.
The other one. So if you put FPGAs and some kind of I/O controller on NIC, now from a DPDK perspective, the question is how do you manage this? So the first thing we need to try and see is how do we do this transparent to the application. So we don't want to change the application so it'll be aware there are two devices out there. So the idea of how do you do transparency, we proposed a new idea along with our colleagues from 6Win. They proposed the same concept of using a wrapper device. So a wrapper device wraps up the two virtual device of a wrapper device, includes those two devices and splits the APIs in between either the ASNIC, the SmartNIC accelerator FPGA, or the SmartNIC IO controller. Those are two PMDs. So the idea behind this is some features can still be implemented in the IO controller. Smart IO controllers also have DPDK acceleration functions, and you can enjoy the best of two worlds. You can enjoy all the features that are in the ASIC and the IO controller, and you can have additional features which are missing and appended using some programmable device. So this wrapper device is not really transparent in the sense that it has some logic embedded in it. It decides feature by feature which one to send to each one. So it's not a generic wrapper for all implementations. You get one programmable device, another IO controller, and you get to match whatever functionality you want to put in each of them. So that's the idea of a wrapper device. So one of the options you can do is you can put the same API into both devices. Maybe you want to program or you put it only onto one device or to the other device, so you have the capability of splitting the APIs as needed. Okay, so now we're going to describe a little bit about what can we do with the SmartNICs. What do we want to accelerate? So the basic acceleration that everybody uses is accelerating the NFV. In each application, if you have virtual machines or you have containers, you have to somehow split the functionality, the packets coming in, into the virtual machines or the containers. So if a packet comes in, you have to inspect it and decide where to send it to. So this is inherent in any virtualized environment. So for this, you have to put usually a virtual switch. The usual virtual switch you use is OVS DPDK, the FDIO virtual, the VPP, or the tungsten fabric virtual routers. Those are the most common virtual routers, but the problem is it eats up CPU resources. So let's assume that you have some high requirements from intensive from processing. So each VNF or virtual machine needs to process something like 40 gig, and just assuming each core provides 10 gig of processing, so you have to dedicate 4 cores to each of the virtual machines, but then you have to have additional 12 cores for the virtual switch. So it has to process, the combined traffic of all the 3 virtual machines, and this sets up a lot of cores. So in some cases, this is, not good. Specifically in the case mentioned before of the edge employments. If you have NFV at the edges, you have a limited number of servers you can fit in, then on your dedicated cores to do whatever the application wants to do and not waste cores just for the virtual switching. So in this case, you can use a SmartNIC to offload the virtual switch itself as much as possible. The packets will reach the Vnfs, but it can help in some of the virtual switching, for example, in classification and whatever features can be offloaded. In this example, we speak about SRV and the PCI pass-through. So if you have a VM or a container that you do not want to go through the virtual switch, sometimes it's a big no-no. We discussed in the morning that this creates problem for, if you want to do the SDN controller wants to do VM migration and all this. This creates a little bit of a bottleneck because the ports that are not going to the virtual switch are not centrally managed by the control entity. The SDN controller, the orchestration, they're not aware, they do not assign specifically those IP addresses and do not manage them. So from an orchestration perspective, this is not the best solution. But this is a reality. If you have an intensive, high-performant VNF, usually right now carriers accept the fact they have to use direct connectivity and bypass the virtual switch. The benefit of that is once you bypass the virtual switch, you have the ability to accelerate the VNF itself. So there was a discussion in the morning using virtual DPA. You can bypass somehow the VNF and go directly to the acceleration in the SmartNIC. But this creates a little bit of a problem because if the virtual switch did some modification to the packets, then the acceleration becomes a little bit of a problem. So you have an entity in the middle that might change the networking. So if you have a direct PCI pass to an SRV, then the VNF can be accelerated by the smart NIC, which is a benefit. If we extend this, a very common use case could be to use a VNF that is out there right now, but rewrite the VNF in the sense that the control plane will be separate, but the data plan can use one of the virtual switches that is already out there. So one of the tasks that sometimes vendors have to do is if they need to rewrite their software in the data path, that's a big thing to use DPDK. It's if they have not written from the beginning the data path using DPDK, changing and moving to DPDK is a big task. So another option is just keep the control layer and use some well-known data path elements such as OVS or VPP, and then you don't need to rewrite your code, you just take whatever is in there. The benefit of that is that all those cores, all those virtual switches use DPDK, and in the DPDK we already have hardware acceleration, and this is a big win-win situation. So one time you write using the DPDK the offloading function, and now it's available to the various virtual switches, and now it can be available to any VNF that needs high processing of networking. Another option of VNF offloading is using representer ports. Representer ports are a little bit complicated in the sense that the traffic flows from the VM or the container to the NIC and then goes back to the OVS, and then the OVS decides if this can be offloaded, and then the rest of the traffic, the rest of the flows will go directly between the virtual machine and the smart NIC, or they keep going to the OVS. If they keep going through the virtual switch, then inherently you waste some cycles, because the packet goes to the smart NIC, goes to the OVS, and goes out the port, so it goes twice. But if this can be offloaded, it makes a big benefit, and if there's no offloading, you waste some PCIe bandwidth of the packets traversing twice. The benefit of this is that you get the best of two worlds. You do get the management of the orchestration, be aware of those switches, and if you want to do VM migration on this and all this management, this can still be provided, but the other benefit is that you can also offload the features of the VNF into the smart NIC. So there is some overhead of managing the representer ports, but if you manage this, you get two benefits. One complication you get is that right now the smart NIC is a slave to two masters. He has to offload the virtual switch for doing the representer ports functionality, but it also has to offload, if we want to, the virtual machine. So we have to find a way for both those DPDKs to share same logic, same offload functions. Now I'm going to go through some examples of typical VNFs, just to name a few. Tap as a service is gaining a lot of interest lately. Tap as a service is just a passive probe or a passive entity that lets all the traffic goes through it. And then if an entity such as a network probe or a network monitor or a lawful intercept point establishes a connectivity and it wants to tap the traffic, then it points to, for this example, an agent that manages the smart NIC, and then it tells, okay, I want to look into a specific something. What is a specific something? A specific flow. Could be the full port, receive or transmit, could be a specific VLAN, or it could be a specific subscriber. So whatever n tuple, you send the command to the switch, and then the switch, the smart NIC, replicates all this traffic. It establishes some kind of a tunnel to this entity, to this maybe network probe, or like a VXLAN tunnel or IPsec tunnel, and then replicates the traffic and sends it to probing for further analysis. So the thing is about this is that this creates an extra bandwidth, and it also requires some very minimal flow classification that could be, n tuple, because you don't know which flow is going to be looked at. So you need some very flexible classification. This is a good example of how a smart NIC can easily do this. Using DPDK, you can use an RTE flow and decide that this RTE flow is replicated. It's easy application for a smart NIC and DPDK. Another application that we're working on this together is virtual BNG or virtual BRAS. Virtual BRAS is the idea is that for managing residential users, you usually have a big router, the big router that assigns you the bandwidth that you want, assigns the IP address, and essentially manages the subscribers at the home. Right now, this is usually done by a fixed router, a big box, usually a Cisco or Juniper router. So the idea is to replace that with some kind of server and some virtual router software, and possibly a smart NIC. So what are the functions of virtual BNG? We have a full slide of next features. We'll dive into this. But essentially, there is a big, right now, replacement that's being done in the network where people are pushing out all the routers, trying to replace them with software. One idea we're showing here is some nice usage that can be done in the telco application is what we call full offload. In this idea, in this concept, the control layer is done by the virtual machine, but then the data path is fully offloaded into the smart NIC, meaning all the functionality of the data path of the virtual BNG is done on the smart NIC. So you have two data paths. You have the data packets going from left to right, going from the homes directly into the virtual firewall and then to the internet, and all the traffic, the packets are flowing to the smart NIC. True enough, the first packet will go to the control layer, to the data path layer, and using some kind of, in this case, RT flow, the consequent packets will flow directly. So just the first packet of each flow go up, and that's it. But then we still have DHCP packets and PPPoE packets and whatever other control packets that are still flowing to the control plane. So this is an interesting application in the sense that it's different than the virtual machines, usually that getting all the traffic into the machine. In this case, you get 100% of 99% of fully offloading all the traffic, and you don't need any CPUs or cores for the data path processing.
Thanks, Barak. So I'll just step on to a couple of more slides and come back. I'll just continue with what Barak was mentioning on the overall requirements. So one that the speaker pointed out was the full offload. So what's the reason that a full offload is preferred is that when we are looking at these kinds of bandwidth, we are talking about 100 Gbps per smart NIC at a minimum, maybe going up to 400 Gbps per smart NIC. And if we look at an architecture like this, where there are maybe 5 or 6 smart NICs, so we are talking about net bandwidth of about 2.4 terabits, a minimum of 600 to sub 1 terabit to close to about 2.4 terabits. So to handle this kind of load, it was kind of felt that a full offload is definitely a better way. And to do this, the design goals, again, as Barak mentioned, control plane packets, yes, and the first packet, and the rest of the control plane needs to be serviced by a control plane VNF. But one of the major design goal was that can cross traffic, say the upstream traffic from, let us say, one user goes out to the network, and then the corresponding downstream traffic, the corresponding session pinning, can it happen inside a given smart NIC itself, so that all the session information, everything is contained, all the statistics, all those collection for a particular user is all contained well within the smart NIC. So there is no need to lift a packet just for some processing into DPDK, and then for some processing back, so we avoid the PCIe double charge. So these are some of the considerations, and as you can see, the other one was about the overall session setup. So when we are talking about this kind of bandwidths, the number of users that would be associated with it scales to millions. So with a few millions, maybe 2 or 3 millions of users, we are talking about a huge volume of number of users coming up, and if there is a failure in the network, number of users who have to be reprogrammed from one NIC to another NIC, from one line to another line. So this requires a lot of intense processing closer to the point of failure. So the closer to the point of failure in this case would be as close in the hardware itself. So this was another reason. Now let me go back to a couple of slides. So with this background, if you look at the Bng requirements. So we have categorized the requirements into two. The ones on the left are kind of the per subscriber scaling requirements. So as I mentioned, the scale is into millions. So all this that we see here in a scale scenario would need to be handled at a few millions. And these are network level aspects which do not need that scale. So the point here is that DPDK does support most of these as offload functions, but then the support across smart NICs is not the same. So for a homogeneous any-to-any kind of a scenario, somebody has a data plane VNF and it can run on SmartNIC 1, it might need some modification to run on SmartNIC 2. But from a telco perspective, a true homogeneity is that a data plane VNF can run seamlessly on more than one SmartNIC. So that is one. And these are the current available DPDK functions that we see. And some, if I take an example of, say, the PPPoE here, some functions do need to be added into DPDK, but mostly they're all available for us to use. Now coming back to a big picture case where we talked about the edge case. So in the edge, we would have multiple VNFs, and potentially each VNF, the ideal scenario is that any of these VNFs works with any of these smart NICs, just like it happens today with the standard NICs. But today it may not be the scenario. Today we would find that a VBNG vendor has a close tie-up with one particular smart NIC, and another, let us say, EPC vendor has a tie-up with another smart NIC, so there's a close coupling. But then from a service provider perspective, it becomes a case of a vendor lock-in, or I cannot make use of the resources across the board. So what we really need is that a resource layer that each of these applications just view the smart NICs as another common resource. And via DPDK, if there is a parity amongst these smart NICs, then the flows can be from SmartNIC 1 or SmartNIC 2, and the packet processing happens in an identical way, whether it is in this SmartNIC or the other SmartNIC. That would be the ideal vision scenario for the telco. I think with this, our presentation is done. We would really welcome you to shoot questions. Yes. Yeah.
I think that in general, telco requirement includes reliability, right? Like short downtime when, for example, replacing software updating. Is it possible to achieve short downtime using SmartNIC?
Okay. So it's a question that, achieving short downtimes or reprogramming? What is the question?
I think that, for example, if operators want to add some features to the network,
yes,
then software have to be updated, and maybe SmartNIC accordingly.
That is true. As Barak already mentioned, with a SmartNIC, be it a CPU-based SmartNIC or an FPGA-based SmartNIC, it is pretty much the same. And definitely with an FPGA-based SmartNIC, it is just like a new software rollout, and the software would contain an FPGA image and would upgrade the FPGA as well.
So first, the concept of a few applications in the same FPGA are already supported today. So one FPGA, one SmartNIC can support a wide variety of applications. Now, if you want to have additional features, along the way, you can easily reprogram the FPGA on the fly and get new features.
On the fly?
On the fly.
And probably there's going to be an afternoon presentation by another, I believe there's a P4-based FPGA, so you can reserve your additional questions for that.
Okay. Thank you.
Thank you. Any other questions?
Yeah, so thank you for talking about this. I think full offload is definitely the way to go. A little bit surprised, actually, that FPGA takes more favor over traditional, like an ARM-based SmartNIC that's already, has DPDK code running in C. Everyone's very familiar with that. I just wanted to get your opinion on the adoption or the interest in having individual telcos write their own FPGA code or own Verilog code. Is that something that people are warming up to at this point?
So our approach in Ethernity is that we provide the code. That's our business. We provide the code, and other approaches are for carriers to program this. I think you're right. This is not an easy task because you need to have some expertise. Our claim to fame is fitting lots of logic into small FPGAs, and it's not an easy task to do.
So then are the carriers given the opportunity to upgrade it later, or do they still?
They come to us. Our approaches come to us. Other approaches are different.
Okay.
There are different approaches. We're just not saying ours is the only approach. But our approach is that we think we have the best expertise. So you want new approach, new functionality, we give it to you.
Okay. So yeah, they can come back to you for if the function's not right. Okay. Great.
Just one question on the kind of separation of control plane and data plane. You seem to be suggesting that the data plane segregation happens at the SmartNIC, but is that not necessarily? That's not necessarily the case. I would have thought in terms of a scaling level that there's going to be applications where you want the data plane running just purely in software. The bandwidth requirements aren't there for going directly onto SmartNIC. So that layer that we were showing at the start, the gRPC layer between control plane Vnfs and data plane Vnfs, that should be the separation point, and there's no reason why the data plane application is a pure software construct, a hybrid construct where part of the pipeline is in hardware and part of it is in software, or the full offload model. I think the DPDK community should be trying to go to that plane that you need to solve all of those. Data plane needs to be all of those things. I don't think it makes sense in a DPDK community environment to say the SmartNIC is the segregation point, because it doesn't. I don't think it will meet everyone's requirements.
No, I'm fully with you on this. We just gave an example, because if you want to do full offload, there has a very specific use case. In the virtual BNG, you have to have all the functionality on the SmartNIC. Usually it's not the case. Maybe you have some software that you need to run. But if you can implement everything, and this is the case we've done with the virtual BIRAS, once you download everything, you gain the benefit of some flows doing the full offload. But I fully agree, if you want to do DPI, for example, and whatever functionality is not available on the SmartNIC should go to the generic virtual switch. This is why it's there, right? We never said we're not taking the virtual switch away or the business. We're just saying that in some cases you can do the full offload. It's definitely not the usual way.
Yeah.
Okay. Thanks,
Thank you.
guys.